faire un tour dans le monde des MNT, des DEM, et puis de voir les mathématiques qui s'y appliquent et comment on est capable d'en retirer des informations assez intéressantes. Fait que c'est le professeur Daya Sagar qui va nous présenter ça, qui est en ce moment en Inde et il est assez tard pour lui. Il est 10h30 là-bas du soir. Qui travaille à l'Institut indien des statistiques, qui a passé un peu de temps au Canada aussi pour un contrat de professionnel ou de postdoc il y a quelques années. Donc je vais lui laisser la parole et nous parler de tout ce qu'il fait comme recherche sur les DEM. So Saya, it's your turn. You can start sharing and start your talk.
Sure. Thank you, Dr. Nicholas, for introducing me in the language of French. And then, though I didn't understand, but I know that he's been introducing about me. So good to see you all. And then I'll start sharing the screen and then I'll start making the presentation. Yeah, this is a nice flyer. It was made and then I could see, and I have posted at different places in my institute. So I'll just put in a slideshow mode and then yes.
Yeah, we can see your screen.
Yeah. So this topic is about mostly about spatial data. A typical spatial data is digital elevation models. I'm sure the people at the Center for Applications of Research in Remote Sensing, CARTEL, the University of Sherbrooke, are quite familiar with digital elevation models. And then this is about processing and analysis of DEMs, in short, via a field called mathematical morphology. And mathematical morphology is more European, but applications of mathematical morphology, in particularly Earth and Planetary Geosciences, we have done some significant work for the last almost 3 decades. And I would like to present some of those results. But if someone is really expecting that there would be some kind of mathematics, and they will be upset because I don't really like to spend more time on explaining the morphological operations in terms of their equations because of short of time. And so just to have a glimpse, and whenever we actually map or try to analyze the features or phenomena or perform some kind of quantitative reasoning, obviously the precise data availability is an important aspect, and this whole work is with an assumption that the digital elevation model that we are processing or analyzing are free from noise. But when you look at the literature, mostly digital elevation models that were acquired through various different mechanisms have come with certain kind of uncertainties. In a way, not all DEMs are equal. And that is where I feel that many people used to ask, and how accurate are the results that you have generated out of the spatial algorithms that you developed using mathematical morphology. My answer used to be like, as long as digital elevation models are free from noise, and all the spatial algorithms that we developed would give very, very accurate results. That was our answer. And then subsequently, to study any spatiotemporal model or the behavior of a specific phenomenon or a process, and we have to look at the data, acquisition of data, then the subsequent ingredients when we talk about some kind of spatial data sciences include information retrieval and information characterization, information reasoning, and modeling, simulation, and visualization. So these are the main ingredients that I mentioned. So why this kind of studies we have to really emphasize. And then subsequently the digital elevation model, we all know that it's an engineering marvel. and we have these DEMs for the whole Earth's terrestrial surface. And then there are various different DEMs, and some are available free of cost. Some are coming with the huge amount of cost, and they are at with different spatial resolutions and temporal resolutions. But we have used multiple DEMs, but I still believe the DEMs that are generated through topographic contours are much more accurate than the DEMs that are developed or generated out of remotely sensed satellite data. Okay, that is one aspect. And then the mathematics that I have been using to process and analyze digital elevation models with a clear goal of getting some scientific outcomes is the mathematical morphology, a field that was invented at Paris School of Mines. There was a school, a center called Center for Mathematical Morphology, which was founded by Professor Georges Matron and John Serra. And so many of you are may be familiar with the Fontainebleau, which is about 80 kilometers away from Paris in France. So in mathematical morphology, actually the data will be investigated with another data. For instance, if we take digital elevation model is as f of xy shown here, and then another data with which we investigate to derive certain scientific outcomes from the digital elevation models, and which I have shown it as an f of xy because we are talking about elevation as a variable across all spatial coordinates represented with xy. And then we investigate that kind of data with another data which we call as a B or a structuring element, and which is flat in nature. And then we can also investigate the DEMs with reference to non-flat structuring elements, which we denote with G. And the entire talk, you would see there is data and there is a probing rule. You can call it as a structuring element or a structuring function. And then data is investigated with another data to address what? And to address the tasks such as information retrieval. What is that very unique information that you can retrieve from digital elevation models? Perhaps topological connectivity networks. Yep.
Yeah, excuse me. We're still on the first slide of your presentation.
So is it not moving? That
no, for us it is not moving actually.
Is it moving?
No, I think you might have to stop sharing and start again, maybe.
I'll do that. Yeah.
We can see the first one again now.
It's in the slideshow mode.
No, we just see the first one. Maybe just don't put it full screen.
How about this? It's in full screen mode.
It's still in the same mode on the. Oh, yeah. Now there is a change. Yeah, it works.
I'm sorry for the disturbance or the confusion. And then, so this is what I was talking, and there are main ingredients in, you say when we deal with digital elevation models with a field of mathematical morphology, and we actually investigate the data with another data, that another data is actually called a probing rule with certain characteristic information. Mostly this characteristic information includes shape, size, orientation, and the origin of the probing rule, which we call it as a structuring element. And then, so why we investigate the data with another data is to address certain tasks like information retrieval and information characterization, and information reasoning, modeling, and simulation and visualization. I could see that if someone asks me, can all these tasks be handled with a single mathematical field, I can really suggest that mathematical morphology is one of those mathematical fields which can address all these basic ingredients of spatial data sciences. So I have just moved the slide, and could you see that the change of slide?
Yes, it works.
Yeah. So
Thanks.
just to give you an idea, in mathematical morphology, mostly in geosciences, it was very popular in petrology, geographic information sciences, geosciences, and remote sensing. And so there are various different morphological operators. I don't go into details of these morphological operators. I can just mention about four fundamental morphological operations or erosion to shrink an object, dilation to expand an object, and the cascade of erosion followed by dilation is called opening, and cascade of dilation followed by erosion is called closing. And these fundamental four morphological transformations are of nonlinear in nature, and because of their nonlinear properties, and these operators or the transformations have a lot of applications across many different fields. I can mention that mathematical morphology is with a small amount of theory, but a large number of applications one can see it. I have applied the very basic binary and grayscale morphological operations in petrology, geographic information science, and remote sensing, and as a specific operation called hit or miss transformation, which is also called a Serras transformation in geomorphology and hydrology, mostly for some kind of template matching and pattern matchings. And there are several other operations which are based on the fundamental four morphological operations, or thinning, thickening, pruning, and they have many applications in hydrology and cartography. And these are some of the operations and their transformations and their the domain application areas, and then major references. This is just for an interest as a reference I have shown it. And as I also mentioned, that essential ingredients to develop any model that leads to behavioral predictions are retrieval of information, quantitative information analysis, quantitative information reasoning, simulation modeling, and spatiotemporal behavior in a kind of attractor construction. So this is the article that about an education column I have published in IEEE Geoscience and Remote Sensing magazine, where the argument was mostly on we have digital elevation models and billions of dollars were spent on generation of these DEMs. But if a researcher has a bit of knowledge in a specific mathematical field, such as mathematical morphology, fuzzy set theory, wavelets, and geostatistics and spatial statistics, or some kind of discrete mathematics, and the way they look at digital elevation model to unravel hidden topological information is entirely different. And that was the argument that I have made it here. But it would be nice if some of the universities like Sherbrooke, University Sherbrooke, can introduce a topic like, mathematical morphology in digital elevation model studies. So this lecture is, I have given enough introduction, but so these kind of statements I want to make, like some applications are glorified due to the robust theory implemented, and some theories are glorified due to their obvious successful applications. I say mathematical morphology is a wonderful theory, which was a more like an European field, but it's slowly getting, gaining popularity in other parts of the world. And then it has large number of applications, particularly when we talk about Earth and Planetary geosciences. So this is about mathematical morphology, a single mathematical field that can address many challenges in spatial data science. And I mentioned that spatial data science, the basic ingredients are retrieval, analysis, reasoning, modeling, and simulation, and of course, visualization. So many used to ask whether this mathematical morphology is an artificial intelligence tool. Yes, indeed, it is an artificial intelligence tool. And there is, what is the gap between the natural and artificial things? Like, so we need mathematical field. And what is that mathematics? And I always choose mathematical morphology because I'm quite familiar with the operations, how they function, and then I can actually think morphologically when we actually address a specific task of the spatial data sciences. And then natural intelligence mostly through logical description by an expert, and computational intelligence such that machines can understand and mimic the logical description given by the domain expert. I can really suggest to the audience that mathematical morphology, take it to heart and start thinking about morphological thinking, develop morphological thinking, and you will really realize that mathematical morphology is indeed a kind of artificial intelligence like domain. So the spatial data, digital elevation models, and what does it have? It has the rich amount but hidden geometric, morphologic, and topologic quantities and associated parameters. And relevant mathematics, having expertise in mathematical morphology and fractal geometry would be a huge advantage to unravel geometric, morphological, and topological quantities. And then science out of the spatial data and spatial information is studying DEMs and then GMT quantities and associated parameters across space-time scales facilitate researchers derive important science outcomes to develop models through which one can better understand the dynamical behaviors of several terrestrial phenomena and process of Earth and planetary surfaces. So we know that there are several different digital elevation models available, and some are synthetic DEMs, Aster DEM, NASA DEM, Shuttle Radar Topographic Mission DEM, Cartosat DEMs. There are a large number of DEMs, but so of late I read an article, a review kind of article written by someone from Mexico, and he has written about not all DEMs are equal, and so each DEM is coming with a certain amount of uncertainties, and those uncertainties of they are like the source material error, and then eventually they actually show that errors in the results that we really try to derive. And then some of the geometric, morphologic, and topologic quantities include peaks, pits, global and local minima and maxima, elevation contours, crenulations, unique valley and ridge connectivity networks, topographic depressions. All these are having lot of geometric vigor, and I feel that morphology can really handle deriving various different measures from the DEM and various different features such as contours, crenulations, and unique valley and ridge connectivity networks and topographic depressions. So, but if someone is interested to know how this mathematical morphology can be seen as an artificial intelligence tool, I would really suggest they should go through the Isabella Bloch and Sammy Blows of Ramianopin Paris. A link is given here. It's such a nice tutorial. You can easily realize that morphology is a kind of artificial intelligence tool. So just to give you an idea of what is this particular talk presents in subsequent slides, and these are the co-founders of mathematical morphology, Georges Mathurin, who is also considered as father of geostatistics, and John Serra, and he is the pillar behind the development of mathematical morphology. And then if you look at some of the synthetic digital elevation models, I have shown this is a synthetic one, and we followed some kind of fractal approaches to generate the outline, and then internal topological region was actually simulated out of certain a sequence of morphological operations, and we simulated a digital elevation model which follows the Hortonian principles. And in turn, I say that this synthetic DEM is similar to the watersheds, hydrological watersheds we actually deal with. So what are the main features that we can derive? Of course, the elevation contours. And then the other features are like unique connectivity networks like river networks and the ridge connectivity networks. And in a larger version, probably you can see blue and green lines. And then we can partition them into watersheds of various different orders. That can be done automatically by following the watershed transformation, which is very popular in mathematical morphology, which has been heavily applied or employed in segmenting the images in a conventional classical images, but applying morphology on digital elevation models and the kind of watersheds that we get are called topological watersheds, which have some connections with hydrological watersheds, but which we still require to explore what are those connections. And then we can also simulate the artificial landscapes. And so by using some skeletonization and reconstruction procedures, and these are some of those snapshots I mentioned here. And this is another case. And then computing the surficial roughness from the digital elevation models. Having the digital elevation models, we know how to partition that DEM into hydrological watersheds, and then within watershed and what kind of roughness is can be measured. And so the roughness measure is a kind of global measure or a directional roughness we can compute. And in all different possible directions, we can compute roughness values. And in turn, we can compute a kind of spectrum of roughness values, and which would give a different kind of insights for the, the geomorphologists and geoscientists. So those studies were also done by using some iterative morphological opening and morphological closings. And morphological opening of multi-scale morphological openings would generate a particular DEM in a sense that it loses information as you increase the cycle of opening operation, and that is to compute the foreground roughness. And the converse is, and applying the closing operation iteratively with increasing cycles, and then you can actually gain energy within the watershed, and then you can compute the background roughness things. And so these are also popular, and that is another case we will cover in the subsequent slides. And then computing the a morphing like sequence. This is a source DEM. Let us assume that this DEM is about a specific region of 100 years back, and this is the DEM after 100 years. And then what exactly has happened in between? Can we really interpolate a sequence of digital elevation models in between year 1 to year 100, and you only have source and target, and you don't have the DEMs, how the terrestrial surface has traversed over a period of time? We can actually compute uh, morphological interpolations in a hierarchical way, and then we can actually show how a morphing like animation, how a source DEM has been slowly transformed into a kind of target DEM, and which is a kind of typical modeling tool. And these are some of, and then when you have a large number of DEMs within a database, and can you pair, can you group the DEMs based on some kind of parameter, probably the proximity, the distance between the DEMs, and which two DEMs are close to each other in terms of distance, like probably morphological distances, and then you can group it in a kind of, best pair. Best pair to worst pairs, and we can actually do that process. That is another case probably I would like to show if time permits. Yeah, this is the overview. We are talking about DEMs and mathematical morphology. I'll show very briefly about a few notations, equations, and transformations. And then I will show some kind of snapshots about how morphological skeletonization has been employed in retrieving the unique networks from digital elevation models, and how DEMs can be partitioned into hydrological watersheds, and then how ranks for pairs of images, a kind of DEM classification. And then quantitative information analysis, we call that as granulometries. If somebody is very familiar with remote sensing, morphology applied to remote sensing, a group of scientists, they spoke a lot about, morphological profiles, extended morphological profiles, mostly for, hyperspectral image classifications. But those morphological profiles are typically the granulometries. This is the word that, originally proposed by Georges Matheron and John Serra. And so these ideas were mostly to quantify the surficial roughness. And then I would like to skip this geodesic spectrum in bottom topographic studies, because for want of time, probably I have to skip that. And this is to actually derive a kind of width function like uh, probably a kind of graph, and a width function of a watershed will explain about it is like a one-dimensional geometric support about a watershed. And so that one-dimensional geometric support has certain limitations, but by following geodesic spectrum based width function would tell us what exactly is happening from one threshold elevation region to another threshold elevation region within the watershed. So the next one is quantitative spatial reasoning. It is more of geo computations and geomatics, mostly for the spatial optimizations. You have multiple watersheds in a kind of basin, and then you want to actually find out which is that watershed located at the strategic location. Then can we do some kind of spatial optimization? And then subsequently, can we deal with which two watersheds are interacting in a much stronger way compared to those watersheds which are having the interactions very feeble? And that is where we employed the spatial interaction modeling studies. And the modeling and visualization, as I have shown, that interpolations between source DM to target DM and how we actually perform morphological interpolations, I will show it. And so this is the general overview, and I would like to go a bit probably quickly to finish it in another probably 20 minutes or 25 minutes to leave it for some question and answer session. So these are the different DEMs, a synthetic DEM, this is a Topsar DEM, and this is a Cartosat DEM, and this is SRTM DEM. This is a Cartosat DEM and their vertical exaggerations. And this is a bottom topographic map of acquired through ground penetrating radar of San Francisco Bay. And this is the DEM with completely noise free DEM, and so which we generated by taking some sparse contours, and then we have interpolated the missing contours between the successive contours, and it is like a low resolution contour map you have, and you are generating a super resolution contour map, DEM from the low resolution contour map. So its corresponding vertical exaggeration is shown here. So these are the founders, and broadly speaking, mathematical morphology can be categorized into binary mathematical morphology. Mostly it deals with black and white features. Like, which are the black and white features in the digital elevation models? When you threshold it to find out what is threshold elevation region, and you can mention based on a specific elevation value. Above this elevation value should be in white shade, and then below specific threshold elevation threshold value should be black, and then you are actually typically converting a function into a kind of a set. So we consider the digital elevation model as a kind of spatial function, and which can be decomposed into maximum possible threshold elevation regions, and in turn you will have all binary threshold elevation regions. You want to work on a spatial function or the decomposed versions of threshold elevation regions which are in binary form. So we have binary mathematical morphology, which offers binary erosion, binary dilation, binary opening, and binary closings. And then we also have grayscale morphology, which works on a kind of neighborhood values, just like a digital image, and where if you treat each grayscale value is a kind of elevation, a kind of relief, and typically that is what is there in digital elevation models. And we have grayscale erosion, grayscale dilation, and grayscale opening and closings. So mind you, all these operations are nonlinear operations. And in a sense, when you perform an erosion operation on a specific object, you get an output. On the output, if you perform a dilation operation, do you get back your original structure? You don't get back your original structure as long as the object that you are investigating is geometrically dissimilar to the probing rule, that is the structuring element BRG that I mentioned at the beginning of the slides. And then the next one is about graphical mathematical morphology. And this is a current advances in advancement in mathematical morphology. Given a region or an image, and they convert into a kind of graph, and then you have graph erosion, graph dilation, and graph opening, and graph closings, and subsequently you have graph based morphological transformations. Adaptive mathematical morphology, like when you are investigating a specific object, which is the right structuring element that you have to choose to investigate that specific object. The choosing the right structuring element actually comes from the field of adaptive mathematical morphology. Right, I have given a long list of transformations here, and see, it is not really sufficient. The time is not sufficient to explain each and everything. And I was telling the other day, Dr. Nicholas, that to talk about mathematical morphology in digital elevation models or in geosciences, it takes about 18 hours of lectures, and so which I can cover very detailed way, probably on like a whiteboard or a blackboard. So this is a list of transformations which I have already shown in the previous slide. And so we talk about spatial objects and spatial fields. Typically, the digital elevation model is a spatial field that is a spatial function. If you are converting that into some kind of black and white threshold elevation regions, and we call them as x, m, b, and these are all some of the notations. This is a spatial field f of x, y, and area under the function. B and g are the structuring elements and structuring functions with which you are investigating the actual functions. And fi and fj are perhaps these are the two spatial functions at two different time periods. And the plus in the open circle is dilation, and minus in the open circle is erosion. And a solid circle is a closing where the dilation followed by erosion is involved. And then the open circle is like an erosion followed by dilation is there. And I don't like to go really into these details because it takes long time to explain those basics. But employing these four fundamental operations, dilation, erosion, opening, and closings, and we can do many of, right from deriving or retrieval of the information to characterization, modeling, and quantitative reasoning. And probably we will go further into those slides. And to give a kind of comparison, on the left panel, you are seeing all binary erosions and binary dilations and binary opening and binary closings. And their counterparts in the grayscale domain is grayscale erosion, grayscale dilation, grayscale opening, and grayscale closings. And we have, their multi-scale versions. When you try to increase the size of B, and with the scale factor called n ranging from 0 to some capital N, and you will see the effects of erosion much faster if you increase the size of B, and effects of dilation much higher when you increase the size of B. In the same way, erosion followed by dilation, it actually smoothens the object, and erosion followed by dilation in the grayscale domain, it smoothens the digital elevation model. Like in the sharp peaks of the mountains will become very smooth and things, and there to the different levels of smoothing, and with the increasing size of B, and you can smoothen the objects or the spatial functions to different higher degrees. And when you smoothen something, you lose information, and that loss of information is a very crucial parameter when you are trying to compute the roughness value of a terrestrial surface. And these are some of the snapshots. These are typically the structuring elements, which are flat structuring element, which we denote with B. And then it has a specific shape and size and origin at the center, and in turn it is symmetric. This is a kind of circle in 8 connectivity grid. A circle in 4 connectivity grid is a kind of rhombus like, which is also symmetric because origin is at the center. And you have asymmetric structuring elements also. It all depends on the type of feature that you want to retrieve from digital elevation model, and you can tune your structuring elements. And these structuring elements are also many a times represented as a non-flat structuring elements. You can see that it is like a structuring function, which is not just flat with zeros and ones. So you can use both flat and non-flat structuring elements to unravel various hidden geometric, morphological, and topological features. And we also have some kind of grayscale erosions by structuring function instead of just structuring element, which is in nature it is flat and symmetric. And we have multi-scale morphological erosions and multi-scale morphological dilations on the spatial functions. And these are again from the fundamental morphological operations, you can derive a skeleton from the digital elevation model. Typically, the skeletal network from digital elevation model is nothing but the valley connectivity network. You invert the DEM and perform the skeletonization. Whatever the network that you get is a kind of ridge connectivity network. And we can also compute for the spatial objects and their spatial functions the roughness values. And we have morphological dilation distances between the objects. What are those objects? Perhaps we can take the hydrological watershed that you have decomposed from digital elevation model or the spatial objects. If you want to find out the distance between the two hydrological watersheds, mostly to find out whether there are any similarities. What is the degree of similarity between, let us say, a watershed xi and a watershed xj, and we can actually compute the morphological distances, and we can actually do the classification of those watersheds in terms of their shapes and sizes. Similarly, we have their more grayscale counterparts, and you have roughness value you can compute, and then subsequently you can compute the interpolations between the two DEMs, two spatial functions. Perhaps it is like two faces, and my face, and then probably Nicholas' face, and between these two faces, and I can hierarchically generate a large number of interpolations, and then I can slowly morph my face into probably the Nicholas face. And these are the ideas coming from morphological interpolations. And in entire morphology, you have dual operations. Erosion is dual to dilation, dilation is dual to erosion. Opening is dual to closing, and closing is dual to opening. And then similarly, you have morphological interpolations, and you have it is dual to its the morphological interpolation shown with a kind of delta. And then you have granulometries and anti-granulometries. Granulometries will quantify the foreground roughness, and anti-granulometries will quantify the background roughness. So the next one is about because I have given some yeah. So I have given some very quick understanding of morphological operations and then transformations and how they will be useful. If somebody is keen, and I would really encourage him or her to look at these YouTube presentations, and which were like almost how on a blackboard one can explain these fundamental morphological operations were shown in these YouTube links. So the next one is to show the applications, and I have given a brief idea about what exactly is mathematical morphology, and I would really recommend people to look at John Serra's Image Analysis and Mathematical Morphology, which he has written in 1982, and subsequently Pierre Wall has written a book, and which is in a, easy to understand way, because he is a kind of agriculture engineer, and he has written it to for those application geoscientists, and so that book can be easily understood. The next one is to just to give an idea, information retrieval. What is that information I want to retrieve from digital elevation model? Very unique networks are the valley connectivity networks and ridge connectivity networks. And the extraction of that was mostly shown in commercial software packages by following Newton's descent properties. But if sometimes the terrain is rather less with less undulations, and if it is not highly hilly terrain, and then many of those ideas or the algorithms available in commercial softwares will fail to extract the true river networks, and that is where this curvature based or the geometry based or morphology based network extraction would really resolve that problem. It is like, are you talking about the fluvial region or tidal region? In you have DEMs of fluvial region and tidal region. In tidal region, extraction of the possible valley connectivity network is a real big challenge when you talk about the ideas available in commercial softwares. But whereas using the concept of skeletonization, we can actually derive these networks irrespective of the terrain type, whether it is fluvial or tidal regions, and they should work fine. And you look at this is the synthetic digital elevation model. A typical valley connectivity network is this. What we have done, and we have actually decomposed it into a kind of threshold elevation region by choosing a specific elevation value as a threshold value. And this is a spatial function, and this is a spatial object, and converting this into skeleton, what it involves some multi-scale erosions and a smoothing of that multi-scale erosion, and you subtract this version from its corresponding erosion, you get some nth level skeletal subsets. and all nth levels are ranging between 0 to capital N. And if you can find out all skeletal subsets of the digital elevation model where n ranging between 0 to capital N, if you take the union of all that, you get a network like this. So that is, I don't want to go beyond that. And if someone wants to see what is its corresponding algorithm, I really recommend them to look at these very basic papers which are written about almost 2 decades ago. And this is the DEM, and the green lines are the valley connectivity networks and the blue lines were ridge connectivity networks. Precisely what we followed here, and the equation that I have shown earlier, that is about the skeletonization equation, and then applied on the synthetic DEM, and invert the DEM and apply the skeletonization, you get the ridge connectivity networks. And then exactly by following some watershed transformation where you find out some topographic depressions or local minima values, and you start uh, dilating that local minima values, and until those dilation versions are extinguishing each other, you can partition the given spatial functions into a topological watersheds. You have here hierarchically partitioned watersheds of various different orders are given here. And again, further one wants to look at how, what is the algorithm that we followed. Typically that is a watershed, morphological watershed algorithm, and one can look at the geophysical research letters paper that I have mentioned somewhere. So this is the same version to have a better visual appeal and the spatial function, a DEM, and then ridge and valley connectivity networks, and then hierarchical watersheds that are partitioned on the spatial function. So can we really generate an artificial landscape? And if you know a specific boundary conditions of a specific watershed, and I have shown that boundary conditions as a kind of Koch quadratic fractal, and then that can be converted into its skeleton. From the it has the skeletal subsets ranging between 0 to capital N. And when you take those all skeletal subsets ranging between order 0 to order capital N, and you get this well connected network, and zeroth level skeletal subsets should be dilated 0 times, and the first level skeletal subsets should be dilated once, and second order skeletal subset should be dilated twice, and capital nth level skeletal subset should be dilated capital N cycles. And then take the union of all those dilated versions of those skeletal subsets ranging between 0 to capital N, and give them certain kind of shades as probably the coding, some color coding or the shading. And then when you put that in a kind of vertical exaggeration form, and you see it a kind of landscape. I would call this as a fractal landscape which will follow all Hortonian laws. And further details can be probably looked at this particular paper which was published in almost more than 2 decades ago. The next level I was talking is about when you have a large number of DEMs in a database, and you can actually taking ith image and the jth image, what is its corresponding rank for that particular pair, ith and jth image pair, and we can compute the infima between ith and jth images, and then suprema between ith and jth images, and then compute their area under the function, and area under the function. Obviously this will be ranging between 0 to 1, because suprema values are always higher than the infima values if they are not equivalent to each other. And then erosion distances and dilation distances, minimum of erosion and dilation, we can actually compute the erosion and dilation distances between ith image to jth image, which were earlier used for computing certain similarity measures, but we have used it for giving a kind of rank for all possible pairs. This is the unified equation that we have followed, and this rank, if it is 1, and we say that ith and jth images are exactly the best pair, and they are, because they are equivalent to each other. If it is, the rank is going towards 0 and it is less dissimilar, less similar, and then that is the worst pair. And so the involved interaction matrices were given here, And again, I would really like to recommend the reader or the audience to look at these papers which are published a few years ago, and one was in IEEE transactions in image processing, and other one is in TGRS thing. So this is, I am not going into again those details, but I'll show the results. And this is a DEM, and with an intention, I made them into four parts, and probably like this is the first quadrant, this is the second quadrant, and third quadrant, and fourth quadrant. And we followed those equations, and we generated a kind of rank for the pairs matrix. And then what is this is F1, F2, F3, and F4. And what are the ranks? And obviously F1 to F1 is 1, and F2 to F2 to itself is 1, and obviously the image to image itself, the rank is the it's just exactly equivalent to each other. But whereas when you look at F1 to F2, what is the rank, and F1 to F3, what is the rank, and F1 to F4, what is the rank? Higher the value, better the pair. And then it's also symmetric, and because from A to B and B to A would be the same, and we could see that these two are the best pair, like probably F1 and F2 are the best pair, and then the worst pair is I think F2 to F3, I believe that is this is the worst pair. And a kind of classification or grouping, or a kind of clustering, we can do it when you are handling a large number of digital elevation models in a database, right? And that is what is mentioned here. When you go to the next level of information analysis, and we are actually using both morphological shape decomposition and granulometries. And very quickly to go, look at these three networks that I have shown here. And if somebody is familiar with, river morphometric studies, Stallers and Horton morphometric studies, they will understand computing the morphometric parameters like bifurcation ratio and mean length ratio and mean area ratios. And they are actually called topological quantities in a physical sense. And looking at these three networks, and all these three networks topologically invariant, in the sense that they are just the same in terms of topology, but geometrically they are differing. And if you look at the hill slope areas are the non-network regions. And then what we want is, see, if a physicist may like to get some kind of power law values, I'm sure that all morphometric topological quantities are indeed a kind of power law values. But a typical geomorphologist may like to see a measure which shows the basic distinction between these three networks and corresponding basins. These three networks are topologically invariant. Morphometric measures are not just sufficient. We require some other approach. And what we have done, and we have constructed a kind of convex hull around these networks, and a typical closed hull by following morphological closing, we have constructed that. And you can see the sequence of the closed hull. How we have done, we have performed closings with increasing cycle, with cycle 1, cycle 10, and cycle 20, like that for highest number of cycle. And the whole network has become like its closed hull region. And now you subtract the network, river network, from that closed hull. It is like taking out the skeleton from the body, and whatever is remained is called, actually in terms of fractal geometry, it is called fat fractals. But in geomorphology, subtracting the river network from the closed hull region, whatever you get is the hill slope region. You pack that hill slope region with a non-overlapping disks, and you can see how we have done by following morphological shape decomposition. A larger portion is this, and then the next level objects are this, and they are all non-overlapping octagonal-like objects. And here the probing rule that we followed is an octagon. Apollonian space is packed with octagons of various different sizes. Same ideas were employed. Non-network space has been packed with the structuring elements of octagonal type of various different sizes. Now you can actually compute the number and radius relationship, and then they will give you the power law value, which is scale invariant but shape dependent. The moment you change the shape of the structuring element, you see a different kind of power law value. So what matters is not just the scale, and the shape matters a lot in most of our studies in digital elevation models. Some of those results were mentioned here. And then here, the roughness of here, whatever was done on a kind of binary images, which are decomposed from digital elevation models. And so when you take the grayscale versions or the spatial functions, DEMs themselves, and by performing some iterative openings and closings, you can transform digital elevation models into darker and brighter regions, openings, recursive openings, and would make the region darker. Recursive closings would make the DEM into brighter, which means you are losing energy here and you are gaining energy here. And the loss of information and gaining of information, and what is the sequence of those loss and gain of information, and which is actually called pattern spectra analysis. I don't go into those details again for the want of time. And you can see them here. The kind of shape that we use to investigate the DEM is a rhombical type, square type, and octagonal type. You can see on the top panels of each of these, it is losing information or it is losing energy with increasing cycle of opening. It is gaining energy with increasing cycle of closings with respect to rhombus. With respect to other structuring elements, we have mentioned this. The loss of information is shown in the pattern spectrum, which is a numerator here, and the total energy under the function, it is the denominator. And then you start computing the probability values, and then P log P, like Shannon's entropy, would get you the uncertainty index, which is actually the roughness value. So the roughness value, again, depending on the type of rule that you have followed. So the roughness value is the shape dependent. So in geomorphology or terrestrial morphological studies, as I mentioned, shape matters a lot. And with each shape, what is the roughness value? What is its corresponding interpretation in terms of terrestrial process involved there in that particular watershed? Similar thing we performed on directional morphological analysis. It is not just a compact symmetric and directions northeast to northwest to south east, and so north south, and we have different directions, four prominent four directions. With each direction, how the roughness values are changing for each of the watershed that is decomposed from the digital elevation model, and then their higher directional roughness value. These are the global roughness values based classification, and higher directional roughness value based classification, and low directional roughness based classification we have done. And we can actually show a spectrum of roughness values. That spectrum comes from various different directions, from this corner to this corner, and then from top to bottom and left to right, and then this corner to this corner. The roughness values are entirely different when you compare with the global roughness values. So that is what is studied here, and global and directional roughness values by using Cartosat DEM. And we have given some evaluations of what would happen when you are performing openings by so many cycles with a specific directional structuring element. Those evaluations were shown here, and again, for the want of time, and I don't want to explain those things in detail, but one can have a look at this particular paper where the classification of geophysical basins from SRTM DEM by using directional granulometries. This would give the whole algorithm in a much simpler form, easy to understand. And this geodesic based spectrum, and I would avoid this because it is as simple as this, and given a DEM, and you can decompose them into the threshold elevation regions. Typically, you have three threshold elevation regions: green region, red region, and cyan region. You have only one region here, which is like a flat basin. You have multiple regions here, and their vertical exaggerations and 3D forms were shown here just for visual appeal. And then the flow fields within that can actually be done with geodesic morphological operations. And then the flow fields within a flat basin, where the elevation values are just the same across the whole region, the topological region, whereas here it is different with three different elevation regions, multiple elevation regions. And then this would actually give us a kind of, we have done that for realistic region. This is San Francisco Bay, and this is for another region, I think this is Santa Cruz DEM and then San Francisco Bay. And this geodesic flow fields would allow us to compute some kind of one-dimensional geometric supports, which would tell us how are the the runoff process and geomorphological process and unit hydrographs can actually be interpreted. But it is entirely through not by width function, but by the geodesic spectrum. The next one is spatial reasoning. If you assume that these are the decomposed watersheds from the digital elevation model, and you want to find out which is that watershed strategically located, and we simply follow some kind of morphological distances between A1 to A2, A1 to A3, and A1 to A10, and it's a kind of matrix because we have 10 watersheds here, and so you get a 10 by 10 interaction matrix. From that you can actually find out which is that watershed located at the strategic location. And so the basic morphological distances were actually given here. This is an object A, AI and AJ. And as you dilate this until this AJ becomes part of that. And what is that minimum number of dilation cycles required to satisfy that property is the dilation distance between AI to AJ. And you keep on dilating it by keeping this stationary. How many dilation cycles are taken to occupy this? And that is the dilation distance between AJ to AI. That is the principle involved in the whole of this spatial optimization process. You can see it here, and there are 66 water bodies. Their corresponding zones of influence are typically watersheds, and then strategically located water body and its corresponding zone of influence are found out. These are the red patches for their corresponding watersheds and the corresponding zone of influence. So the process involved there is, you can see a simple animation here. There are three objects, and from here to here, and what is the minimum number of dilation cycles required with what directional structuring element would actually explain us the further spatial optimization process. And I will stop this animation. And then interactions when you have multiple watersheds. The typical equations that we have followed is gravity models, but the gravity model that we have used here is asymmetric gravity model because location significance is important, and then dilation distances are not symmetric like the Euclidean distances. In turn, the whole gravity model based interaction thing is become a asymmetric kind of thing. The force of interaction between A to B is doesn't necessarily be equivalent to the force of interaction between B to A. So that is the idea, and for that we have actually shown in a synthetic way, but taking all states of India as the watersheds, and then so the close by states are well interacting, and the sparser watersheds are less interacting, and this was done actually based on the modified gravity model. The equations I have not explained in a proper way, but again you can have a look at that in the whole algorithm, and some results were given in this particular IEEE TETC paper, right? And then the next level is to show that morphological interpolations and converting the point specific data into polygonal form, which has no actually connection with the digital elevation models, but I will show only for those things which have got some kind of connection with the digital elevation models. Look at this, it's a flooding process. The flooding from the points are the point specific, and some points are getting propagated much faster, some points are getting propagated much slower. And then when such a thing happens, and how we deal with mostly for simulation of or you say a generation of cartograms, variable specific cartograms. And so the last one is about morphological interpolations. Let us assume that these are synthetic, the numerical arrays representing elevation values of two different digital elevation models. And then how we compute infima is the point-wise minimum, and the suprema is point-wise maximum. So these are the infima and suprema functions. And then on that, the median function needs to be computed. The median function will be computed as infima of Fi and Fj. These are the Fi and Fj. You dilate that, and suprema has to be eroded. and then take these two functions and then find out what is the infima between these two functions. You do that by increasing the size of n from 0 to 1, 1 to 2, 2 to 3 up to capital N, and then you can actually compute the median function between these two spatial functions. That is the principle involved. If you are using the flat structuring element and if you are using the non-flat structuring element, you get a different kind of transitions. So with the flat structuring element, the transition is much smoother than the non-flat structuring element. You can see those two things in these two prominent papers, and which were published in 2010 and 2018 subsequently. This is the source DEM and this is the target DEM. A typical interpolation that we have computed between these two based on those equations is this. And between source and interpolation, you will compute another interpolation. Interpolation and the target, you compute another interpolation. And this goes in a hierarchical way until there is no further scope for you to interpolate one more between the successive interpolated sequence, right? And then this is the algorithm, how it is computed. And again, this is based on this particular 2010 paper. And then you can see with the flat structuring element, a sequence of interpolated thing. This is the source and this is the target. In between, so many interpolated sequences, sequential interpolated regions were shown, computed. And this is based on the flat structuring element. This is based on the non-flat structuring element. Again, source and target. You have a sequence of interpolated computed images. And then we can see with non-flat flat structuring element and how the morphing from source to target. And this is with 8 connectivity flat structuring element. And this is with non-flat structuring element. So the morphing of it is like if you have a sand dune DEMs. Sand dunes are very, morphology of sand dunes is highly time varying. And so you can actually taking by taking multi-temporal sand dune DEMs, and you can actually study the morphological changes that have happened over a period of time within the DEMs of the sand dune regions. So with all that, and so what is the way forward? I could show one the spatiotemporal behavior of terrestrial phenomena and dynamical behavior of terrestrial process. Can this be really done by following those algorithms that I have shown for information retrieval, information analysis, information reasoning, modeling, and simulation and visualization? So can we address these aspects? The open challenge is Earth surficial phenomena include numerous geomorphological features. It's like not considering, constructing feature specific and process specific attractors to better understand the dynamical behaviors of each and every geomorphological feature and phenomenon is really a challenge. And I could see that a robust mathematical theory that Earth and planetary science communities need to pay more attention to deal with this type of challenge. So with this, some of these key references that I show, and if someone is interested, and they can look at this particular book that I published in 2013, and most of these results were shown, except those which are published after 2013. And so somebody is interested in the actual theory of mathematical morphology. Highly advanced one is the special issue, filtering and segmentation with mathematical morphology, which was the special issue was published in 2012 for IEEE signal processing selected topics. And this is an open book writing announcement, and I know that so many of your colleagues are accomplished enough to write a book, and just look at this. Probably I'll share this with Dr. The hosts here, and then they can circulate this. This is just have a look at it, and so very interesting topics were covered in this book series. And so before I leave it for question and answer session, probably I took slightly more time. And so I'm really grateful for IEEE GRSS for giving me this GRSS DL chip. So actually my colleague is ailing, and so he has been battling in the hospital for the last 10 days. And so I dedicate this talk to my colleague, Professor Kaushik Majumdar, and a great colleague and a well-known computational neuroscientist. Unfortunately, he is having a serious health problems for the last 10 days, and he's really battling. So, so now it's open for question and answer session. Thank you for your patience. And so I will leave it to the audience. If they have any questions, I would be more than happy to answer them. Yeah.
Thank you very
Thank
much,
you very
Daya.
much, Aya. Yeah.
There was quite a lot of information there.
Thank you. Thank you.
Yeah, it was very interesting. I've seen that people have started to leave a bit as for us they are getting back to work. But if some people have a question for Daya, Julien maybe, or
Yes, and then where is the meeting? Is the meeting?
otherwise I would have
Let's stop sharing. Yeah.
Yes, I
yeah.
have a
Otherwise I
question.
would have like one very simple question for you.
Yeah.
Yeah, Julien.
Yeah, I was just thanks for the talk, Professor Sagar. I just wanted to know if you can comment quickly on fractal geometries and if they're useful in your line of work in mathematical morphology.
Yeah. Yes. Actually, the fractal ideas and mathematical morphology have several connections. So one very basic connection I would always tell is, the founders of mathematical morphology and founder of fractal geometry, Professor Mandelbrot and Georges Mathurin. These two are the students of the same professor, Professor Paul Levy. Paul Levy is considered as a father of probability, and these two have come from the same school. And so that is one. And the fractal geometry, I would actually rate probably it's off the record, and I see mathematical morphology is with more mathematical basis. And compared to the fractal geometry, in fractal geometry, mostly what we look at is we look for some kind of scale invariant parameters, power law relationships, fractal dimensions, and fractal dimensions are indeed the roughness values of a given object. But why those roughness values are, I have seen the box counting method is a one popular method to compute the fractal dimension. And but in mathematical morphology, you have a choice of choosing the probing rule. Those probing rules, a family of probing rules you can choose. It doesn't necessarily be a simple box, as is the case with fractal geometry. But it's very nice to, put a marriage between mathematical morphology and fractal geometry. There are many connections. I actually had shown a lot of interest during the beginning of my research career, and both fractal geometry and mathematical morphology I used to look at. But that's how you have seen many of my papers, and the case studies are mostly on the quadric fractals, but the entire operation that I performed are the morphological operations on that. There are very good connections, and but I can actually suggest a few papers. So some of them are my own papers, where morphology and fractal geometry were shown some kind of relationships. Yes.
Mm. Well, I'm really looking to maybe listening to your talks on YouTube. So maybe if we can access the slides, so I can have I can
Of course,
access the
yes, and
link that you gave, because
I will share with him. So
yes.
right away I'll share with him, and then it would be nice if I can, or you few people can come down here, and then we can have a. Probably I'll think about running a school here, and actually I ran a school in 2015 for about 2 weeks summer school, and out of 60 lectures, I was giving about almost 35 lectures on morphology in geosciences specifically, and in geographic information science. In GIS, there are many, many applications of morphology.
Yeah, I think it's a especially, I think it was the one of the last slide when you were saying that there's like open question and how we can link it to, modeling and all that
Yes,
stuff. And for
yes,
in our line of work, where I work on snow, and there were some interest in fractal dimension in the early 2000, but people weren't really able to really link it and use them. So I'm
yeah,
kind of looking forward for maybe because you were talking about roughness at some point, and
Yes.
And now you can use them in watershed. I think maybe they're
Exactly.
because the fractal dimension, you find the scale, but after that it was difficult for us to really use them. So
True.
but
True.
yeah, thanks for your talk.
True. No, so this question I always used to ask myself, is a terrestrial surface going from very complex to regularity, from irregular to regular, or regular to irregular? So if we have multiple multi-temporal data, particularly the digital elevation models, we can really quantify those things by computing either fractal dimensions or the roughness values. And then we can show that the roughness value is it's getting smoother and smoother over a period of time, but that happens within watershed. But I don't know about the snow kind of surface, probably glaciers. But it's very interesting to look at. There is Kellen Whipple, and he has done a lot of work on the icebergs and using hypsometric integrals and those things. Yeah.
All right, thank you.
Yeah, thank you very much. And I'll share these slides, both PPT and PDF files. And so we will see for some kind of future interactions, but keep writing to me. And so I would like to attend all the MIDI map lectures from now onwards.
All right, thanks.
Thank you very much, Nicholas, Dr.
Thank you,
Nicholas,
Nick.
and thank you very much for arranging my talk. Yeah.
Thank you. I might have like some very quick question.
Yeah.
At first, you were saying that there are many types of sources of DEMs, and each kind of DEMs has kind of its own uncertainties. I was just wondering, how did you manage those uncertainties, and like, will you manage to have kind of the same end results regardless of the DM that you use first as your data source, or are your end results are going to be very different because of those very different uncertainties?
Yeah. So for the reason of uncertainties existing in DEMs derived from remotely sensed data, mostly we end up showing some kind of toy model and a synthetic DEM. Because I have not seen any DEM with free of noise. And so the moment you fix that noise, or you fill that particular gap within a DEM, and the end results would be entirely different from what exactly is there on compared to what exactly is there on the ground.
Mm.
And sometimes the anthropogenically generated features like roads, buildings, and industries and trees and all that, we are getting the height of the tree and not the actual height of on the ground.
Mm.
What we want is the elevation at the ground point, not at the elevation of the treetop. So if you take any DEM generated out of optical images, and we are actually making many mistakes there. We are actually not computing the roughness of the terrestrial surface. We are computing the roughness of the the canopy, tree canopies on top of it. So that to address that, and I would say probably SAR based DEMs are more meaningful.
Mm-hmm.
But again, and I was talking to the SRTM team leader, Dr. Paul Rosen, and he also mentioned that there are many uncertainties in shuttle radar topographic mission things. But of late now, people are using LiDAR DEMs, and I believe they are very accurate and very high resolution, and even Tandem X from German Space Agency DLR.
Yeah.
I was told, but it is not a freely available data, and we need to purchase that. And someone told me that Tandem X DEMs are really compared to relatively very accurate. Yeah.
Nice, thanks. Well, I think it's getting quite late for you, and people are starting to
Yes,
get back to
and
work. Yeah.
yeah, it is
So
midnight here, and then
yeah.
I'll ask my son to fetch me because Nicholas knows and how dangerous it is in the nights in India. So though it is
Yeah.
not that dangerous in Bangalore, but so I would like to avoid there's some stray dogs walking on the road. I'll call my son and he'll come by car and then he'll fetch me.
Well, thank you
Nice,
very
and
much
I
for your
want to
talk,
meet you
Daya.
sometime and we will see a way.
It's been a pleasure to listen to you and to learn about mathematical morphology.
Thank you.
Thank you very
I will
much.
share, and what all that I have, I will share. The book and all that I will share.
Yeah, great. And for the
Happy.
others, like everything will be put like
Yes,
on
yes.
the Cartel website,
Yes, yes.
so that you can access the information and learn a bit more if you want to.
Sure, sure.
Well, thank you very much. And
Thank you.
well, Daya, have a good evening, and a good night.
Thank you so much. Thank you so
Thank
much.
you.
Yeah,
Thank you.
yeah. We'll
See you.
keep in touch. Yeah, bye bye. I'll stop, man.